Okay, we're looking at Chapter 8, which deals with molecular orbitals and how they're going to help us understand our understanding of all the things that we've actually been looking at thus far in the semester. All right, so what I'm talking about, we actually introduced the concept of a bond last chapter. Like if we were looking at just a Lewis structure of hydrogen, we were noticing that that line represented two electrons that are in a bond that is holding those two hydrogens together. And both hydrogens think they own both those electrons, makes it very happy. To a degree, that bond is what we're looking at. It is a orbital, kind of like our atomic orbitals were, but we're going to see that that's a molecular orbital. It's got some electrons in it. That's what we're studying in this chapter, is what that overlap actually is. Now, the little diagram they have here, it is kind of showing our concept is we have our spherical orbital overlap with a spherical orbital, and this overlap is what creates a bond. Now, to a degree, mathematically, what it actually ends up looking like, if we think about that one hydrogen having a wave function and the other hydrogen having a wave function, and they get close enough, they're going to overlap. And we get an overall constructive interference that's even taller. So a more stable wave function where those two added together. That's what we're seeing here. That low energy is a more stable mathematical wave function. It is the molecular orbital. All right, so before we start explaining what the heck we're doing here, let's talk about what we're going to see is happening on all of our molecular orbitals. All right. First thing to notice is we are going to get what we call a linear combination of atomic orbitals. That's where the LCAO comes from. Linear combination of atomic orbitals. Now, the overlap always happens like it does in A. If you look, A is looking at like two p orbitals from two different atoms. The overlap happens directly between the two nuclei. It's never cockeyed. It's never like this. This is doesn't happen. The overlap has to happen along a line between the two nuclei. Now that's really easy if we're dealing with an s orbital, because s orbitals were just spheres. They're always going to overlap the most right between the two. But p orbitals, the orientation's important. And that's what they're showing here. So that's a restriction we're going to place on. All right, now we can get a lot of different types of orbitals. Now, what I mean by different types of orbitals is we can get different type of molecular orbitals by overlapping different type of atomic orbitals. They could be a pair of S's, could be an S and a P, could be a couple P's. Technically, it happens with D's as well, but the overlap is always happening directly between the nucleus. And anytime that overlap happens, we call that molecular orbital a sigma bond. Now, it is as simple as this. If you have a Lewis structure and you've done something up, doesn't matter what the Lewis structure is, that single line is represented as a sigma bond, because that's how all of the first single bonds are always found. They're always found as sigma bonds. All right, along with sigma bonds, we have what we're going to call pi bonds. Now, these only really happen between p orbitals or things along the lines of p orbitals. And the overlap here happens kind of like, think about the p orbitals being parallel to one another, and the overlap happens when these two overlap. Oop. I have no idea what I did there. That's better. All right. So the overlap happens like that, and it's what we call a pi bond. Now, when this actually forms, that creates an overlap above and below that line between the two nuclei. It's always perfectly parallel. And this is also why, if you remember back when we were first talking about Lewis structures, if I had a dibromo or two bromines off of a double bond like that, this bond could not rotate. So this and this molecule were two totally different things. And the reason it can't rotate is because the only way for this thing to rotate is for those bonds to no longer be parallel. They'd have to, one of them would have to rotate. That would break that pi bond. The only way it can happen is to break the pi bond. All right. When we see a Lewis structure, it's really easy to tell what's going on. Whenever you see a line, whenever you represent a bond, one of those lines is definitely a sigma. If there's only one line, that is only one sigma bond. If there's two, one of them's a sigma, one of them's a pi. If there's three, there's one sigma and there's two pi's. Never anything more than a single, double, or triple bond. So you only have one sigma and up to two pi's maximum, but that's all there ever is. There's never any actual need to actually figure it out. There's never actually a need to see it's just nothing but pi bonds. You at least have one sigma if the atoms are bonded, and as many as two extra pi bonds. But we can tell that by just looking at a Lewis structure. Like on this, if I had a question how many pi bonds there are, we really are just counting the second lines of any double bonds. On this molecule, there are two pi bonds. Sigma bonds, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sigmas. And something that we actually see pop up quite a bit where people are trying to fool you on it, then you might see what they call condensed structure. Now what we're showing here is the hydrogen bonds, the carbon-hydrogen bonds are not explicitly drawn. So if you saw that and now we're asked how many sigma bonds, you might just count just those two. But it turns out around this carbon there are 3 CHs. On this one there's 2 CHs, and on this one there's 3 CHs. They just weren't drawn. That's that condensed structure. So on that structure there's actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sigma bonds. But we really are just doing a Lewis structure and just flat out counting the bonds to figure out which ones are pi's and which ones are sigmas. All right, we have a small problem though. When we overlap this with what we learned in the past with the type of atomic orbitals we have a small problem. Now, I got a drawing here that's supposed to represent water. Where this is coming from, if you think about just a hydrogen atom and its electron configuration, it just had a single electron in a 1s orbital. Oxygen, though, the valence shell, we had 2s2 and then 2p6. No, too many. 2p4. I can make that prettier. Right? Now, we got that right off our periodic table. Speaking of periodic table, I want to make sure I had one handy here. All right. Now, what that means is, in that valence orbital, our orbital diagram, we had s orbitals, and then we had our p orbitals. 1, 2, 3, 4. So apparently what happens when the overlap is that p orbital and that p orbital overlap with the s orbitals of the hydrogen. So this is a p orbital from oxygen, that's a p orbital from oxygen, and this is an s orbital, and this is an s orbital. All right, that's all well and good, but we have a dilemma. The orientation of our p orbitals were along Cartesian coordinates, so x, y, and z. So if this was the x and this is the y, this was the z. Well, that means that these two p orbitals should be about 90 degrees from each other, which means a molecule like H2O should have a bond angle of about 90 degrees. Yet, last chapter, with valence shell electron pair repulsion theory, we found that that was closer to 109. So we have a discrepancy here. The p orbitals and VSEPR theory do not necessarily line up together. So we have to actually figure out what's going on here to help merge these two. Because this whole idea here that I have on this page with just a p orbital, that's actually not what happens. There's something slightly trickier that occurs. All right, what the trick is we need to somehow get 4 groups coming off of a central atom. So if you think about it, on an oxygen atom, you had your s orbitals and your p orbitals. To get the 4 groups, like VSEPR theory had, we have to somehow combine those 4. Somehow add the s and the p's together. Well, ironically, that's exactly what we do. We really do just add those orbitals together. It's a mathematical function, but we are able to do that. And we create what we call hybrid orbitals. Now, a simple hybrid orbital can be seen with something like this. So what I have there is an s orbital and a p orbital. Now, the colors are there to show that the p orbital has different phases in it. That's that twist in the field. Well, when they add together, the s being totally in one phase is going to make one side expand and the other side decrease. So you could think about them adding together to give you something like this. The left side got smaller, the right side got bigger. Weird thing is, there was two ways to do that math. So you just decide, when we actually did that math before, we just decided which side was in phase and which one's the other. So why the reason they're drawing two of these is there's two different ways of getting that solution. But either way, you get two weird shaped orbitals, one with a big lobe on one side and a small lobe on the other, and the other one an exact mirror of it. Well, the neat thing is, I'm going to erase what I put on this screen here. Oh, and I went too far. We have an s orbital, and this is one of our p orbitals. I'm going to put the other two here. And we just added them together. This is what we're going to call an sp orbital. And since we added two of these together, we actually get two sp orbitals. So I'm going to just draw a box representing our two sp orbitals. Now, the p orbitals, the other p orbitals are still there. They're just higher up in energy. We're ignoring them right now. But those two sp orbitals are now going to get as far away from each other as possible, and they are going to get that 180-degree bond angle. All right, if we go bigger than that, we actually start to see some weird rules. Now, the neat thing is we have all these rules that define it, but really all this really tells us is you're going to find a Lewis structure. And if this is a Lewis structure I'm looking at, and I just wrote this one up there, this has nothing to do with the rules. I found a Lewis structure that had 4 groups coming off of it. So, since this particular carbon has 4 things it's bonded to, I need to combine the 4 lowest orbitals. That'll be the s and the p's. And when I overlap those, it's going to make 4 degenerate meaning exact same level, so exact same energy, but they will now be called sp3 hybrid orbitals. Now, the neat thing is how the math works. If I were to actually look at those 3 p orbitals and that s orbital, and then remember the p orbitals are arranged in Cartesian coordinates, and if I were to add them all up and divide it all out and do the math, I do get sp looking hybrid orbitals, big lobe, small lobe, but they will be oriented exactly like they are expected to be in a tetrahedron. So all 4 will get as far away from each other as possible. So it merges what we saw with our atomic orbitals with what we saw with our valence shell electron pair repulsion theory, VSEPR theory. So it actually merges those together. Now the neat thing is that it works on almost any number. So you're just going to add up what you need. You're going to take the atomic orbitals that you need to make the bonding groups you need and create hybrid orbitals based on that. And it really is as simple as this. We have an s and a p orbital. If I want to make 2 bonding groups, I just take the 2 lowest energy orbitals. That would be one of the s's. That would be the s and one of the p's. Add them together, make sp hybrid orbitals. The other 2 p orbitals are still there, exactly where they were. They're just not going to be part of a trio anymore. All right, so every single time, we're simply going to just get a Lewis structure and figure out what we need to combine. If we need 3 groups, we'll add another p orbital to it. If we need 4 groups, we're going to add a 4th, and so on and so forth. All right, so how do we figure this out anytime? If I'm looking at something that like boron trihydride and I want to know what hybridization it is, my first step is always figure out the Lewis structure. So valence electrons, I have 3 and I have 1, so I got a grand total of 6. So I'll have the boron surrounded by the 3 hydrogens, and I'm out of electrons. I get a trigonal planar structure. I have formal charges that are all fine, but that particular bromine has just 3 groups around it, so I need to combine my 3 lowest orbitals and make sp2 hybrid orbitals. All right, when we actually have a Lewis structure, we really can do that in every single case. Turns out all 3 of these molecules, and even the 2 carbons on that last one, every single central atom here needs sp3 hybrid orbitals because there's 1 group, 2 groups, 3 groups. Even though it's a double bond, we count it as 1 bonding group. So we need sp2 hybrid orbitals to do that. Same with this middle one, the CH2O, 1, 2, 3 groups. And either one of these carbons, 1, 2, 3 groups. All three of those, you need sp2 hybrid orbitals to make it work. You do the Lewis structure and just count the bonding groups. All right, how about these? All right, if we count around, it's 1, 2, 3, 4, 5 groups. Same as this, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. These all need 5 orbitals. Well, if I'm thinking about my orbital diagram, if I combine my s and a p's, that only brings me up to 4 groups. So how do I get the 5th? Well, what's up here? What's above a p orbital? D orbitals. Now, mathematically, I can grab them all, but I don't need to. I only need to grab 5 groups. So I'm going to take my s, all 3 of those p's, and 1 d orbital, make an sp3d hybrid orbital. Now, the other 4 d orbitals are up there, unattached, and they're not doing anything. The only ones I care about, those bottom ones. But I just need to grab enough to actually get the groups. So if I went around like this, I could say S, P, 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 D, S, P, 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 D. All 3 of these need sp3d hybrid orbitals. Now the neat thing about this, when they actually do the math on combining all 5 of those orbitals, they get the orientation we expect. The sp3ds actually match up perfectly with Vesper theory, where we have some that are 90 degrees to each other, some that are 120 degrees to each other. But it matches up perfectly what valence shell electron pair repulsion theory actually told us. All right, so what happens if we need one more? We just add another D. Now, the nice thing is we don't see anything above this, but mathematically we could combine these up to, it is just a mathematical equation. So in theory, there is an sp3d5. It's just that we don't see that in nature. We don't see anything more than 6 things coming off a central atom. That's also why back when we were actually doing our Lewis structures, we didn't have anything above AX6 octahedral. Just turns out to make octahedral, you need sp3d2 hybrid orbitals. All right, so how are we going to apply this? Well, back in the last chapter, when we were introducing Vesper theory, we actually introduced this nice little chart that had our bonding families. Well, we immediately advanced that to actually come up with, I don't even have the chart here, do I? Well, it was the chart with all of our shapes. So the AX2 and then AX3, and there was AX2E, but it had our names as well. Well, it turns out everything in that linear family needs sp hybrid orbitals. Everything here needs sp2. All of these need sp3. All of these need sp3d, and all of these need sp3d2. So we will always do the same thing. We're going to find our Lewis structure. Once we have our Lewis structure, we can figure out what the hybridization that's necessary. All right, so let's figure out what the hybridization is on something. If it is just a sulfate ion, our first thing is to figure out the Lewis structure of sulfate. Valence electrons all together, let's see, that'd be 32. And we've done this one a few times. So I'll have 2 oxygens that are single bonded and 2 oxygens that have double bonds and just a pair of electrons. We did that because it got the formal charges on 2 of the oxygens to be 0, this one and this one, and the sulfur had a formal charge 0, but each of these 2 oxygens had a -1 formal charge. We had a -2 written out there. All right, figure out the hybridization. We figure out our Lewis structure and we count the groups. 1, 2, 3, 4. This is AX4. It is tetrahedral. Has 109.5 degree bond angles, and it needs sp3 hybridization. And if I want to add to this, there are 4 sigma bonds and 2 pi bonds. And there is resonance. Those pi bonds move around. All right, how about another one? Selenium tetrafluoride. All right, selenium has actually got 6 valence electrons. Each of those has 7, so this has 34 valence electrons. So I'll put the selenium in the middle, surround it by my fluorines that are following the octet rule and good formal charges. So a bunch of single bonds, a bunch of lone electrons. This would get me up to 32 valence electrons. So I'll put the 34 right there. And that gets me arranged in space and distributed the remaining electrons. And if I check, all my formal charges are 0. So that is an acceptable structure for selenium tetrafluoride. Shape-wise, it's AX4E. That is also known as seesaw. Has 2 different bond angles, 90 degrees and 120. And it has sp3d hybridization necessary. S, P, 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 D. 5 groups. All right. When we have multiple bonds, we have an interesting little thing that pops up. This is a rehash of what we talked about in previous chapter. That double bond doesn't really rotate, but we want to talk about more the nature of what that double bond is. Because, well, if we think about it this way, that particular carbon, to actually work like that, would need to have some sp3 or sp2 hybrid orbitals. And then it has that p orbital left over. Well, this other one also has that p orbital there as well. So that bond, that pi bond, must be happening from those 2 p orbitals. It does give us a neat little picture. It looks something like this. All right. Now, what this does is it makes a pretty interesting little geometrical fact for things with double bonds. Now, that pi bond, we talked about this before, has to overlap where those 2 are parallel to one another. Well, more importantly, it's perpendicular to these other 2 carbons, or the other 2 bonds that are off that. All right, so what that does is it forces this atom and this atom and this atom and this atom and this atom to all be on the same plane. They're perfectly flat. So when I back it up to that previous slide, that molecule is perfectly flat. All 4 of those hydrogens are on a plane along with those 2 carbons. And the only way for it to rotate and break any of that is to actually break the double bond. All right, let's try another one of these with hybridization, because this is a sulfite. So we have SO3 2-. So let's see, that is 26 valence electrons. Yeah. So O and S and O and O. Right there brings me up to 26 valence electrons. Looks like 27. Yeah. All right. Now, if I were to check the Lewis structures or the formal charges right now, I have -1, -1, and -1, and 6, -1, 2, 3, 4, 5, +1. Well, I don't like all those negatives and positives, so I'm going to make at least 2 of them go away. Because what I'm going to do, erase those 2, make a bond here. Ooh, I tried to erase, didn't fully erase. Pretend that's not there. I'll erase this one. All right, that now has a formal charge of 0. This sulfur also has a formal charge of 0. That is actually a better molecule. All right, hybridization. The pi bond doesn't really affect the hybridization. We have 1, 2, 3, 4 groups. It is trigonal pyramid, but it needs sp3 hybrid orbitals. All right, we have a small little dilemma now that we're going to look at. It's going to help us explain a few neat things. Now, what we're talking about here is what the nature of that sigma bond is. All right, now we defined it as just a simple thing like this. We take an orbital and we overlap it. Take another orbital. These are atomic orbitals. For the sake of argument, let's just say they're s orbitals, because those are the simple ones they overlap. When they overlapped, they created a molecular orbital, and we introduced the letter sigma to signify that. All right, now this is the result of math. It's just where those overlap in phase with one another and create a bonding molecular orbital. All right, weird thing that happens though. Because math is the way math works, you might have been able to add them up where they are not in phase. It'd be like, I don't know, you want to go to Orlando and you start driving north instead of south. It'd be the wrong way of doing it, but that's kind of what happens. Mathematically, it has to be a possibility. So up here, higher in energy, where the two atoms are or the two atomic orbitals are trying to pull apart, or maybe think of being added out of phase, we have an anti-bonding orbital. We're still going to call it a sigma, but we're going to put a star on it. Now, what it actually translates to, where this is an overlap, so you got the two atoms, or the two atomic orbitals getting overlapped and creating that overlap. This, they're kind of repelling each other. So there's the central of the atom. I'll put the nuclei here. But this is repelled. Now, no reason to believe it's important because both of them exist. This one's lower in energy, and we're going to put electrons down here before we start putting any up here. So it's perfectly okay that it's there. It's just that it mathematically it exists. All right, the reason this is kind of important, it helps us understand some really interesting things. Namely, how why certain atoms and certain molecules are, well, why they respond to magnetic fields. We actually call it paramagnetism. Now, the really weird one is, turns out oxygen, O2, we get it as liquefied and pour it between some pretty strong magnets, it will actually respond to the magnetic field. It actually is slightly magnetic. Now that's kind of weird because if we look at the Lewis structure of O2, we would predict a sigma orbital with 2 electrons in it and a pi orbital with 2 electrons in it. Now, typically, things that have fully paired up electrons do not have any paramagnetic properties. Paramagnetic properties happen because of electron orbitals being partially full or unshared electrons. Big reason why some of our metals actually respond that way is because that D block, they're actually not very full. Anytime we have unpaired electrons, you have the ability to respond to magnetism. Now, this isn't the same as being magnetic. It's just that they would be able to respond to a magnet. All right, so if oxygen is paramagnetic, does this molecular orbital theory help us explain this little discrepancy? Because this would seem to imply everything's paired up. Well, it turns out it does. All right. So we're going to talk about the nature of these and look at some of the mathematical equations first. All right, so we have our sigma and that sigma star. This is that thing I was showing you before. A little bit better pictures, in my opinion, because my sketching is terrible, but your book did a pretty good job with this. So we have sigma overlapping. We have the sigma star out of phase, higher in energy. All right, that's what we get when we actually overlap s orbitals. Turns out we get the same thing if we overlap with p orbitals. As long as the p orbitals are in phase and the overlap happens directly between, we still get sigma and sigma star. Now, technically, it would have been a little bit nicer if these had been reversed, so we had that sigma lower in energy than a sigma star, but they're actually just showing you what they actually look like. There's that little node actually repelling the 2 orbitals. Now, this is the one that's preferred. If we're trying to make a bond, that's where we see the electrons go first. All right, but here's the dilemma. If this is one of our p orbitals, we know for sure the other p orbital is there, and the other one's coming straight up out of the wall at us. So they can't actually all 3 overlap and make sigma bonds. The other 2 must make pi's. Now, that does mean that one of them does overlap like this, and it does make a pi. There is the mathematical possibility they're out of phase, makes the pi star. But if these are along the y-axis, there's also some coming out of you in the z-axis. So there's another orbital, it'd be kind of like right here on top of us. So there are actually two pi orbitals that are like 90 degrees from each other. Therefore, there's two pi star orbitals. So another way to see it, if we looked at all three of our p orbitals on atom A and all three of our p orbitals in atom B, we have two that overlap to create sigmas, and then you have two that overlap to create pi's. Those three and those three make these six when they form that overlap. All right, now we have a small, neat little situation going on here. For a given atom, say like oxygen, for instance, we could actually put this together and see why it has paramagnetic properties. Now, if it is oxygen, I have 6 electrons over here, I have 6 electrons over here. I need to put 12 of these. So got 3 here already. There's 4, 5, 6, 7, 8, 9, 10, 11, and 12. And you notice how those two are not paired. There are individual orbitals. So way back, if I go back up here, turns out when we said this right here, that wasn't the case. It turns out those two electrons are in two separate pi orbitals. They're just degenerate to one another. One's kind of out of the plane with the other. That's the better way to think about that. That's why it has that paramagnetic properties. All right, what else can this tell us? Well, there is a few neat things it can tell. Like right here we have hydrogen, very simple molecule. 2 electrons go in, 2 electrons down here. If we actually talked about it and said HH, we'd say it had a single bond, one bond. All right, well, what happens if I change this to a positive ion? Well, it just removes an electron from there, right? We would only have 1 electron in the entire atom. Wouldn't you see how that makes this orbital less full? So a hydrogen-hydrogen cation bond would be slightly weaker than this? Yeah. All right, how about change that to, actually I'll do it this way. Get rid of that. Change it to a negative. That means adding an electron. If I add an electron, I'm actually having to add it to that orbital that's putting a node between it and trying to rip it apart. That would also make the atom weaker, or the bond weaker. So on H2, we can actually see why an ion, positive or negative, is less stable, because it's actually weakening the bond that much more. Now we can even do one step further. Does this actually help us to understand why things like helium don't bond? Well, yeah, it does, because helium has 2 electrons, helium has 2 electrons, go in there. As much as this atom wants to hold it together, this one wants to rip it apart. All right, turns out what we were just explaining, we have a mathematical phrase we can look at. We call it bond order. Now, when the bond order is looked at for something like just hydrogen, we really can just look at the 2 hydrogens and say that has a bond order of 1, because it has 1 bond between it. But when the bond order is not so clear, like when there's something that we know there can't be a Lewis structure, or like what we just did in the previous slide with like an H2 minus, we get our bond order slightly different. We're going to add up all the electrons that are bonding electrons. We're going to subtract all the anti-bonding electrons. I'm going to do this, bond star electrons, and then we're going to divide that value by 2. So on this one, this helium on this page, He2, we would have 2 minus 2 divided by 2. Well, that's 0. So that actually says the bond order of helium-2 is 0. So there is no bond. Now, if I go back to that H2 minus, I'm going to go back up a page because we left it on here. what we could do to get the bond order there is say that there are 2 bonding electrons, those 2, minus that 1 anti-bonding electron, divided by 2. So this has a bond order of 1/2. It's allowed to be a fraction. That is kind of like saying the bond is about half the strength of as it was as H2. All right, turns out we can apply this to more complex diatomic molecules. We just have to add our p orbitals into them. We got to actually finish that full diagram. Well, let me back up here to how we have to add this full diagram in here. All right, as pretty as this all is, turns out we get a weird problem that occurs. Oh, my whole page just went away. The weird problem occurs, I'm just going to circle in here. This orbital right here moves on us ever so slightly as we're actually filling the atom. When there's fewer electrons in there, as in we have fewer valence electrons, this thing actually goes higher up. And as we start to add more and more electrons, it drops back down. Well, what we see is some weird little trend. That's what they're showing here. It's way high up if you're talking about diatomic lithium, and then it drops and drops and drops and drops. And it's more normal when we have the 3 on the right side of the periodic table that have more valence electrons. So oxygen, diatomic chlorine, and neon have the sigma filled before the pi's. All the rest, you fill those pi orbitals before the sigmas. Just how that influence is. But it's kind of weird to even know this, because if we think about it, if we were trying to talk about a covalent bond between 2 lithiums, well, lithium only has 1 valence electron. So diatomic lithium, they're both down here. How do we even know much about that? Same with beryllium, that just is 4. Still not affecting us here. Boron gets us up to 6. And carbon gets us up to 8. Now what's interesting is none of those 4 really exist. Can't really make diatomic molecules out of any one of those things. So it's all theory at best anyway. But nitrogen can be diatomic, and oxygen can be diatomic, and fluoride can be diatomic. And we can do Lewis structures for those. Neon, not so much, right? And we'll see why. All right, let's see about this. If I were to take those 5 and those 5 and put all 10 electrons in here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have them all in there. Now, what I'm going to do is figure out the bond order here. I'm going to put it down here at the bottom. All right, I'm not going to erase that. I'm going to put it down here at the bottom. So I have these 2 bonding orbitals and those 4. So I have, that's bonding orbitals. So I have 8 bonding electrons and just those 2 antibonding divided by 2. So this has a bond order of 3, which we would predict it's got a triple bond. O2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So bonding electrons is still 8, 2, 4, 6, 8. Non-bonding or antibonding, 2, 4, divided by 2, has a bond order of 2. And then diatomic chlorine, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 8 minus 6 over 2, bond order of 1. And then if I were to do neon, everything fills. This becomes 8 minus 8 over 2. But we can use that to break the bond order. Now where it comes in a little bit more handy, things like this, where we talked about the paramedic. All right, so where this gets to be kind of weird is, if you look at this, I got a bond energy of nitrogen. Very high, makes sense. Diatomic nitrogen has a triple bond. So we would expect that to be a heck of a lot stronger than O2, which has a double bond. All right, but if you look here, we're making cations out of both of them. By removing an electron here, if you look, it makes the bond weaker. See how that energy drops? Yet on O2, if we remove an electron, it made the bond stronger. Those seem to be contradictory. We can make sense out of that if we look at those molecular orbitals. All right, we're going to do oxygen first because it's the one that fills up those orbitals like we first introduced them. What I mean by that, we have sigma and sigma star from the s orbitals, and then the p orbitals create a sigma, and then 2 pi orbitals, and then our pi star, and then our sigma star. All right, now we already did the bond order of that. That was 2. Matter of fact, this one we did already, and it was a bond order 3. So let's see what O2 positive has for a bond order. So only thing I'm going to do is take those 6 electrons and 6 electrons, so the 12 valence electrons, I'm going to subtract 1. So I'm only going to put 11 in here. 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, if you think about it, we removed one right here. If you think about that also, we moved it from an anti-bonding orbital. So one of the electrons that makes the bond slightly weaker is not there anymore. Mathematical bond order-wise, we have 2, 4, 6, 8 bonding orbitals. We have 2, 3 anti-bonding orbitals divided by 2. This has a bond order 2.5. The bond got stronger because we removed an electron from an anti-bonding orbital. Now, nitrogen has one minor difference when we start filling up the boxes. We're going to have our sigma and sigma star, but we're going to fill a pi orbital before the sigma because this has fewer electrons. Then we have our sigma star and our pi star. And we have 10 electrons together. The positive removes 1, so I'm going to put 9 in here. 1, 2, 3, 4, 5, 6, 7, 8, 9. If you notice this time, the electron that was removed came out of a bonding orbital. That's why it got weaker. Because it turns out we only have 2, 4, 6, 7 electrons in bonding, minus those 2 anti-bonding. This also has a bond order of 2.5. The bond got weaker. All right, you're going to see something neat. If you play around with these a lot, you'll never see a bond order above 3. Gets back to there's never more than a triple bond. And it goes down from there, and it can go down as low as 0, which is what you get when you get 2 nonmetals to bond. All right, now after this, your OpenStax book talks a bit about using the molecular orbitals to explain conductivity. Turns out there's a little bit of flaw in this thinking and how it gets expanded to some of the more advanced topics. So we're going to leave it off. So once you get done with your diatomic descriptions, you're done with this.